Welcome to the first lecture video for Calculus 2. At this point in your calculus career, you have a basic understanding of limits, derivatives, and integrals. In Chapter 7, we'll take the basic differentiation techniques that you know, such as the power rule, the product rule, the quotient rule, and basic integration techniques, such as making a U substitution, and apply these techniques to transcendental functions, which include exponential functions, logarithmic functions, and inverse trigonometric functions. We will begin our approach to this task by first reviewing the algebra of inverse functions and then examining the calculus of inverse functions. So everything in this first video should be a review of algebra. Let's begin with a definition. The inverse function of f of x, denoted f inverse of x, reverses the action of the original function by applying appropriate inverse operations in the correct order. Now, we can visualize the relationship between a function and its inverse in the context of a mapping. If we assume that these two circles represent sets, we can label the first set as the domain of the function f and the second circle as the range of the function f. Now, the function f takes a point from the domain of f, we'll call it a, applies operations to that input, and pairs it up with some sort of output in the range. Now, observing this relationship, we could say f of a equals b, and we could also say that the ordered pair ab is on the graph of f of x. Then an inverse function is going to reverse this action. Where a function ends, an inverse function begins. So the range of f is the starting point or the domain of f inverse. And the domain of f is the range of f inverse. F inverse will take the output b, apply operations in the correct order, and match it up with output A. We could make the observation f inverse of b is equal to A, and the ordered pair BA is on the graph of f inverse of x. So f inverse not only reverses all of the operations of the original function, it reverses all of the ordered pairs and in general switches the domain and range. Now, there is one very important indicator for whether a function is invertible or not. So let's examine the prerequisite conditions for invertibility. First of all, a function is 1 to 1. And you'll often see me abbreviate that just 1-1, if every value of the domain corresponds to a unique value of the range. Now, if I pause right there for a minute, we could observe this is the simple definition of a function. Every input has a unique output. But I'm going to add to that and make it a more stringent definition to define a one-to-one function. And every value of the range corresponds to a unique value of the domain. So the ordered pairs are unique and one-to-one. No x's ever repeat, no y's ever repeat. Now, a function is invertible if it is one-to-one. That is, when I reverse it, the result will also be a function. Now, not every function that we reverse is actually invertible. A function may not be invertible on its entire domain. It may be necessary to restrict the domain to subintervals in order to find an inverse. Let's consider example 1. Are the following functions one-to-one and therefore invertible? If they're not one-to-one, we will identify the intervals or the subintervals for which the function has an inverse. Now let me remind you of both the vertical and the horizontal line test. The function in example A passes the vertical line test. That is, I cannot construct a vertical line that intersects the graph in more than one place. So by the vertical line test, we know that the graph is a function. Now, if we rotate this test 90 degrees, Notice this function does not pass the horizontal line test. That is, I can find a horizontal line that intersects the graph in more than one point. This identifies two different x's with the same y. So it does not pass the horizontal line test. Therefore, this function is not one-to-one. If it's not one-to-one, it is not invertible on its entire domain. The domain of this particular function is -infinity to infinity. However, we can find subintervals that are one-to-one, that is, they do pass the horizontal line test, on which we can invert the function. For example, if I look at the left half of the graph, starting at the vertex and moving to the left, that branch itself is invertible. So this graph is invertible or one-to-one on the subinterval from -infinity to 0. We can also see that from the vertex, moving to the right, we have a branch that passes the horizontal line test. Therefore, it is one-to-one and invertible. So we could say also on the subinterval from 0 to infinity. So even though the function is not invertible on its entire domain from -infinity to infinity, there are subintervals of the domain that pass the horizontal line test, which indicate that the function is one-to-one on those intervals and therefore invertible. What that means again is when I reverse the function, the result will pass the vertical line test, that is, itself will be a function. Let's look at the next example. You probably recognize this as a sine wave. If we run the vertical line test, that is, we look to see if we can intersect the graph in more than one point with a vertical line, this graph passes. So the vertical line indicates this is a function. That is, every value of the domain has a unique member or a unique pair or a unique partner from the range. However, it's pretty easy to see that this function does not pass the horizontal line test. That is, I can find a horizontal line that intersects the graph in more than one point. In fact, a horizontal line would intersect in an infinite number of points. So this graph is definitely not one-to-one. Therefore, it is not invertible on its entire domain, which, by the way, is -infinity to infinity. However, if we restrict the domain, we can find some intervals where the function is invertible or one-to-one. Now, as a sine wave, generally the place where we restrict the domain is from -π/2 to π/2. Now, there's a lot of different ways to do this, but that's generally the one that we focus on for inverting the sine wave. But you could certainly observe that we have another branch of the function out here that passes the horizontal line test. So we could say it's also invertible from π/2 to 3π/2. And we could continue this process. We'll just say ... There would be an infinite number of subintervals where this function is invertible. But again, we generally focus on the branch between -π/2 and π/2 for invertibility. And we'll talk more about that later in the class. Let's look at the last example. This is a cubic polynomial. This guy does pass the vertical line test, therefore it is a function. But once again, we see it does not pass the horizontal line test. It is not one-to-one and therefore not invertible on its entire domain, which again is -infinity to infinity. So we could restrict the domain. I can look at this first branch over here and say it is invertible on the subinterval from -infinity to -1. We could also see that between x, remember I'm using x values here to indicate the subintervals, it is also invertible on the subinterval from -1 to 1. And also this last branch of the graph, which goes from 1 to infinity is 1 to 1 and therefore invertible. So all three of these examples were functions. That is, they all passed the vertical line test. None of them passed the horizontal line test, so they were not 1 to 1 and invertible on their entire domains. But we could certainly find subintervals where the branch of the function was 1 to 1 and therefore invertible. Now, with the understanding that an inverse function reverses the graph or reverses the action of the original function, this also has implications for the graphs of inverse functions. Note, the graph of f of x and f inverse of x reflect each other across the line y equals x. Y equals x is our basic identity line, or the line that goes right through the center of the coordinate plane. Let's examine example 2. The graph of a function is given. Restrict the domain and construct the graph of the inverse function by reflecting f of x across the line y equals x. We want to identify the domain and range of f and f inverse. So again, in example 2a, we have a quadratic function. The domain of this quadratic function is negative infinity to infinity. And as we saw from the previous example, it is not invertible on its entire domain. However, we can restrict the domain, and we're just going to use the right half. We're going to restrict the domain to 0 to infinity. So I'm going to call this the restricted domain 0 to infinity. If we restrict the domain to 0 to infinity, then we will be able to invert it. That is, when I reflect it across that dashed purple line there, y equals x, the result will also be a function, that is, it will pass the vertical line test. Now, this particular graph is pretty close to the line y equals x, but I'm going to construct its mirror image reflection across that line y equals x, and we'll have the resulting inverse function. Now let me backtrack just a little bit. I do need to acknowledge the range of the original function. The range there was 0 to infinity. So the red curve is our function f, and our reflected orange curve here is f inverse. So the domain of f inverse is x equals 0 to infinity, and the range y equals 0 to infinity as well. You may recognize that red curve, or the entire blue curve, as the function x squared, our basic quadratic function. The inverse function is very easily square root of x. But again, f of x equals x squared is not invertible on its entire domain, only when we restrict the domain. Notice if I did not restrict the domain and I reflected that entire parabola across the line y equals x, the resulting graph, that sideways parabola, would not pass the vertical line test. That is, it would no longer be a function. So it is necessary to restrict the domain in order to have an inverse function that is, in fact, a function. Okay, looking closely at the graph of example B, hopefully you recognize the nature of this graph as the tangent function. This is, let me call it f of x. This is the graph of tangent of x. Now, it's easiest to express the domain using set builder notation. We could say the domain is the set of all x, such that x does not equal, so what I'm going to do here is exclude the locations of those asymptotes. They do not belong to the domain. The first asymptote occurs at pi over 2. The next one is pi units later. So we could say the first one, or at least the first one I'm going to use, is pi over 2 plus any multiple of pi, where k is an integer. So we're excluding the locations of all of the asymptotes. Now, this graph does not pass the horizontal line test, so it is not invertible on its entire domain. However, you know we have an inverse tangent function, right? So how do we do it? Well, we restrict the domain of tangent to a branch that is 1 to 1 and therefore invertible. The most convenient branch to use is this guy right here in the middle. So our restricted domain, I'll just call it the restricted D, is from negative pi over 2 to pi over 2. Make sure you get parentheses on the endpoints there because there are asymptotes on those endpoints. Those are not part of the domain. The range of our tangent function is from negative infinity to infinity. Now, to reflect this graph across our mirror, y equals x, I'm first going to reflect the asymptotes. Notice the asymptote at pi over 2. If I reflect that, it goes from being the function x equals pi over 2 to y equals pi over 2. So I'm going to have 1 at negative pi over 2 and 1 at pi over 2. So this would be the asymptote y equals pi over 2 and y equals negative pi over 2. Then the inverse function is going to have the same basic nature as the original, but it's going to be reversed. So it's going to look something like this. I think I can do a better job. Let me try that again. My scales are different on the x and the y. Okay, a little better. So that is our inverse function. You can call it arctangent or you can call it inverse tangent. Now notice the domain for our inverse function is negative infinity to infinity, and the range is from negative pi over 2 to pi over 2. Observe how the domain and range have switched from the original function to the inverse function. Okay, let's try one more. On example C, hopefully you recognize this graph. This would be the cosine wave. The domain of our original cosine wave is negative infinity to infinity, and the range is from negative 1 to 1. However, we do need to restrict the domain so that we have a branch that is 1 to 1 and therefore invertible. So in general, for cosine, even though there's a lot of different branches here that are 1 to 1 and invertible, the customary one to use is the one from 0 to pi. So the restricted domain, I'll call it restricted D, is 0 to pi. Notice the brackets there because the endpoints are included. Now, if you have a hard time figuring out what the reflection looks like across that line y equals x, one technique you can use, which relates back up here to one of our first observations, is that ordered pairs reverse from a function to its inverse. So on this example, I could choose this point, which is ordered pair 0, 1, and switch it to ordered pair 1, 0. Again, recognizing our scales are a little bit different, 1, 0 be approximately in this location. If I choose this point on the original function, that's pi negative 1, we're going to switch that to negative 1 pi. So negative 1 and about 3.14. Then we're going to connect our dots with a very similar pattern of the original, and you've got the graph of your inverse function. So f inverse of x, you can write it as inverse cosine or you can write it as arc cosine. Now, notice the domain of this function. The domain of inverse cosine is going to be the range of the original function. And the range of inverse cosine is going to be the domain of the original function. So everything, ordered pairs, the graph, the domain and range all switch. Once we know that a function is invertible and we can examine the relationship between the graphs, what if we start with a function and we want to find the inverse function? Well, to find f inverse, given f of x, we're going to use the switch and solve technique. That is, we're going to switch x and y and solve for y. So let's suppose that we want to find f inverse of x if we have f of x equals 2x minus 3. So I'm going to start with the original function, f of x equals the square root of 2x minus 3. And I'm going to rewrite it in terms of the two original variables. So I'm going to take it out of function notation and replace f of x with y. Then I'm simply going to switch x and y and rewrite it as x equals the square root of 2y minus 3. So that reversing of the variables symbolically switches the domain and range. Then I'm going to solve for y. So to solve for y, in this case, we'd need to square both sides. And observe, as I solve for y, I'm identifying all of the inverse operations and in the correct order. Notice to solve for y, the next thing we would need to do is add 3 to both sides, and then finally divide both sides by 2. So we'd have x squared plus 3 divided by 2 equals y. Then I could go back to inverse function notation. I'm going to replace y with f inverse of x. And I'm switching the sides here as well, x squared plus 3 over 2. That is my inverse function. Now, going back to the original function, f of x, which was our square root function, the domain of this function occurs where that radicand is either positive or 0. So if I solve for x, we can see the domain here is x greater than or equal to 3/2. Or in interval notation, that's from 3/2 to infinity. Think about the graph of this radical function. The range would be 0 to infinity. And if you're rusty on that, you can certainly graph the function on your calculator and verify the domain and range. Now, the inverse function, which is just a quadratic function or a parabola, is going to have a domain from negative infinity to infinity. However, we know that's not one-to-one, so we could restrict, let me finish writing the function here. We could restrict the domain, I'm going to call it a restricted domain, from 0 to infinity, so that it is one-to-one and invertible. Notice if I look at this as a quadratic function, I'm going to think of it as x squared over 2 plus 3/2. It's a basic parabola that's been shifted up the y-axis by 3/2 of a unit. So my range is going to go from the vertex at 3/2 on the y-axis up to infinity. So once again, you can see that the domain and range have switched there. Again, I'm moving quickly because this is a review of algebra, but if you're a little bit rusty on that, I recommend that you graph those two functions on your calculator and observe the relationship between their domain and range. Let's try this again. Find the inverse function g inverse of x given g of x equals x plus 5 over x plus 2. State the domain and range of each function. So let's begin by taking the function g of x out of function notation into variable notation. Then I'm going to switch x and y. So we get x equals y plus 5 over y plus 2. And then I'm going to solve for y. Now the first thing I need to do to solve for y is to multiply both sides by y plus 2. And then I'm going to distribute the x on the left. So we have xy plus 2x equals y plus 5. Now I'm going to collect the terms that have a y on the left and the terms that don't have a y on the right. We'd end up with xy minus y equals 5 minus 2x. Then on the left side, we could factor out a y. And finally, we could solve for y by dividing both sides by x minus 1. And we have our inverse function, 5 minus 2x over x minus 1. So both functions are rational functions. Let's observe how the domain and range switch. So our original function was a rational function, x plus 5 over x plus 2. Notice the vertical asymptote for this rational function, remember that's where the denominator is equal to 0, is x equals negative 2, and the horizontal asymptote, notice the degrees are equal, so we take the ratio of leading coefficients, y equals 1. Might be a good time to go back and review rational functions. So the domain for f of x is going to be from negative infinity to negative 2 and negative 2 to infinity. That is on either side of that vertical asymptote. And the range is going to be from negative infinity to the horizontal asymptote at 1 and 1 to infinity. Let's observe how all of this reverses for our inverse function that we found, which is 5 minus 2x over x minus 1. If we look at the vertical asymptote, that is the 0 of the denominator, we'd find it's x equals 1. And the horizontal asymptote, again, because the degree of the top and the bottom are equal, we take the ratio of leading coefficients, we would end up with y equals 2. Whoops, negative 2. Now, the domain is going to be on either side of our vertical asymptote, negative infinity to 1 and 1 to infinity. And the range will be above and below our horizontal asymptote, negative infinity to negative 2 and negative 2 to infinity. Feel free to graph that on your calculator and observe the domain and the range have completely switched. You can also see a relationship between your vertical and horizontal asymptotes. They have also been reflected across that line, y equals x. The last thing that we want to review as far as the algebra of inverse functions goes is verifying inverse functions. Recall that inverse functions satisfy both of the following: f of f inverse of x equals x, and f inverse of f of x equals x. Notice we're composing our function and the inverse function and obtaining a property of inverse functions. So a quick look at this on the mapping. Here's the domain of f, here's the range of f, and we know this reverses. This is the domain of f inverse and the range of f inverse. Now, if I take a point x in the domain of f and I apply the function f, I'm going to get some sort of output over here. We'll call it f of x. If I immediately apply the inverse function to that, I'm going to end up right back where I began. So whatever the input is, it matches the output. That's what I'm looking for to verify inverse functions. So let's try that with the example functions we've been working with. Verify that f of x equals square root of 2x minus 3 and f inverse of x equals x squared plus 3 over 2 are inverses. So I want to figure out both directions of the composition. So I'm going to first find f of f inverse of x. So f is going to hang out and wait patiently while I insert f inverse. I'm going to put the function rule right here. And then I'm going to plug this into the function f where I see the variable. So we have the square root of 2 times our new argument, x squared plus 3 over 2 minus 3. Now, remember, this is a composition. Another way to write this, if you want to come back up here, we're looking at f composed with f inverse of x and f inverse composed with f of x. That's the skill we're applying, in case you needed that review. Now, as we simplify here, notice we end up with the 2's canceling first, the 3's canceling next, and the square root and the square canceling as well. So the input turns out to be the output, but that is not a sufficient proof. We have to show this in both directions. So I'm also going to evaluate f inverse of f of x. So this time, f inverse is going to be my step 2. My step 1 is to replace f with its function rule. And then we're going to plug this into the inverse function where we see the variable. So we have the square root of 2x minus 3 squared plus 3 divided by 2. Notice how all of our inverse operations still pair up, but they're going to do so in a different order this time than they did on the first time around. So beginning with squaring a square root, those are inverse functions, and the square root cancels. The negative 3 and positive 3 cancel next, and multiplying by 2 and dividing by 2 cancels as well. So once again, we see the input is the same as the output. We can say therefore, the 3 little dots mean therefore, f and f inverse are in fact inverse functions. That's good because we called that second one F inverse. Okay, let's try this same technique with our rational functions. This one will be just a little bit more algebraically intense. So we have h of x and h inverse. So I'm going to start by evaluating h of h inverse of x. So we'll replace h inverse in the argument position here with its function rule, 5 minus 2x over x plus 2. Now, we're going to plug this new argument into the function h where we see a variable. So you can think about plugging that argument into those two circles. We're going to end up with 5 minus 2x over x plus 2 plus 5 over the same argument, 5 minus 2x over x plus 2 plus 2. Our goal is to simplify this. We're not going to make it equal x. We're looking to see, is it going to be equal to x? So to simplify a complex fraction like this, an easy way to do it is to simply multiply the top and the bottom by our lowest common denominator, which in this case is x plus 2. So I'm going to take this x plus 2 and I'm going to distribute it to that first term. Notice if I did that, the x plus 2's would cancel, leaving behind 5 minus 2x in the top. When I distribute to the second term, we simply end up with 5 times the quantity x plus 2. We'll do the same thing in the denominator. That is, we will distribute the x plus 2 to both terms in the denominator, noticing that the x plus 2 cancels from that first term, and we're going to multiply by 2 for the second term. Okay, now let's break up those parentheses with the distributive property. So we have plus 5x plus 10. Breaking up parentheses in the bottom, we have here plus 2x plus 4. When we simplify, we end up with, in the top, 3x plus 15, and in the bottom, 9. Observe, this is not equal to plain old x. When we compose these functions, we do not get an x. This means that these are not inverse functions. The good news is I don't have to compose them in the other direction because I've already disproved one of these tenets. Both of these have to be satisfied in order for it to be a set of inverse functions. And because one direction is not satisfied, we can make our conclusion. Therefore, h, or let's say the function 5 minus 2x, we'll do the first one here, x plus 5 over x plus 2, and let's just call it g, 5 minus 2x over x plus 2 are not inverse functions. So that notation is a bit misleading. Okay, so this completes our review of the algebra of inverse functions. In the next video, we'll begin to examine the calculus of inverse functions. This also might be a good time for you to go back and thank your STEM college algebra teacher for all that they taught you, because that was a quick, fast and furious, and detailed review. I'll see you in the next video.